All right, topic 6.1, circular motion. You need a data booklet and your notebook. To start, we have this first equation, v equals omega times r. V is the linear speed or tangential velocity equals omega. Omega is angular speed or angular velocity times r, which is either the radius of the circular path taken by the object, or it's the displacement vector of the object. A equals v squared over r, centripetal acceleration, v squared over r. Centripetal acceleration also equals 4 pi squared times r divided by t squared, where t squared is the period of the motion. Centripetal force, F equals mv squared over r. The other equation is m omega squared over r, and again, omega is angular speed or angular velocity. So a particle is said to be in uniform circular motion if it travels in a circle or along an arc with a constant speed v. So imagine I have this object is traveling in a uniform circle of radius r. As it does, it has this velocity vector. I want you to copy this diagram. Observe that this velocity vector is always tangent to the circle. It's always touching in one place, this circle. So my velocity vector is in red. The radius of the circle is in orange. And then I can lay it down on an xy plane. Know that the magnitude of the velocity vector is not changing. It's only the direction that changes. There is acceleration with constant speed. This is a new idea. To prove to you that there is acceleration even though the speed is constant, we will look at two snapshots of this object's velocity when it's in two different locations, and I'm going to call one of those vectors v1, and when it's in the second position it's v2. And so we know that acceleration is a change in velocity over some unit of time, v2 minus v1. So I will do some vector analysis, my head to tail method, and I can see that the change in velocity vector then points in. The direction of acceleration for an object's rotating in a circle or revolving around something is always toward the center of the circle. That is known as centripetal acceleration. So if you want, copy the vectors here. Centripetal means center seeking. So how does the centripetal acceleration depend on r and the speed? To explore this, we define the centripetal force, F sub c, as m times a sub c, where a sub c is centripetal acceleration. Picture yourself as a passenger in a car that is rounding a left turn. The sharper the turn, the harder you and your door push against each other. The smaller the radius, the bigger the centripetal force. The faster the turn, the harder you and the door push against each other. So it's higher speed, bigger force. Let's define period is the time for one complete revolution. Frequency measured in hertz, that's the SI, or reciprocal seconds. Hertz is the same thing as seconds to the -1. Frequency is the number of cycles, oscillations, repetitions, revolutions that occur each second, per second. The period and frequency are inverses of each other. So frequency is 1 over the period, or period is 1 over the frequency. Traveling in a complete circle, an object completes one revolution, one trip around the circle. So for a circle of radius 1 unit, the distance traveled by the object is 2 pi. Which is 1 revolution equals 2 pi radians. Radians doesn't stand for radius. Rad stands for radians, where you have 2 pi radians equals 360 degrees. That's how many radians, rads, are in a circle. That's how many degrees are in a circle. 1 revolution, 2 pi rad. So sometimes the period of a revolution is given rather than the velocity. If we know the circumference, then we know everything about the speed. Because speed is distance over time, the distance traveled by an object in circular motion is 2 pi r over capital T. Thus, v squared is 4 pi squared r squared over t squared, such that the centripetal acceleration equals v squared over r, or 4 pi squared r squared over t squared over r. The r's cancel, and we are left with this expression for centripetal acceleration. And here we have Albert, the physics cat, who was not harmed in the making of this video. We're going to draw a free body diagram, so please copy this, A, B, C, D. Imagine I have an object and it's spinning in a vertical circle. Always, always, for an object that's rotating or revolving, the net force is the centripetal force. So let's analyze the net force acting on the object in directions A, B, C, D. Okay, so always centripetal force, center seeking force, it goes towards the middle. I have tension. Tension always goes towards the middle. So F sub C and tension always point in, always center seeking. Okay, then we have the force of gravity in this position acting on the object going down. I build my net force equation. Everything going in the same direction as net force is positive. F sub C equals tension plus the weight for position A. If I solve for tension, tension equals F sub C minus W. All right, if the object is in position C or B, because it's pretty much the same, then I have the force of gravity acting down. Oops, I want to do this in blue. W going down. I have tension again as the center, and the centripetal force, center. In this case, the weight is perpendicular. So for positions B or C, F sub C equals T. Let's see what happens to the object when it's in the D position. Okay, so again, center seeking force, that's always the net force, F sub C going to the center. Tension, always also to the center, and the weight now is in the opposite direction, W going down. So I build my net force equation, F sub C equals tension is positive because it's in the same direction, minus W. If I solve then for tension, tension equals F sub C plus W. Therefore, the highest tension is in position D. At the bottom of the vertical path, tension is greatest, highest at D. And we will go over this again, very important. So always for an object in uniform circular motion, the net force is the centripetal force, the center seeking force. The minimum velocity at the top of the path is the velocity required for the centripetal force to at least equal the force of gravity. That means the centripetal acceleration at the top should equal g. That's the minimum amount of acceleration needed. And centripetal acceleration is v squared over r. Therefore, the minimum speed at the top of this vertical circle is g times r to the 1/2 power. Energy is always conserved. So what forms of mechanical energy are present at the top and bottom of the path? And that must mean they're equal to each other. So at the top, energy is conserved. So the energy I have at the top should be equal to the energy at the bottom of the circular path. At the top, the object has its 1/2 mv, the velocity at the top squared, plus mg2r. This is the gravitational potential energy at the top. Notice it's 2r because I have a radius here and a radius here. So it has this amount of minimum potential energy. It doesn't matter how high up the circular path is, the object can't escape the circle, okay? So this energy at the top must equal the speed, the kinetic energy at the bottom. That means that the energy is conserved. 1/2 mv squared at the top plus mg2r at the top equals 1/2 mv squared at the bottom. Okay, really quick, airplanes can do 3 maneuvers while traveling. You may have to know these: roll, yaw, pitch. Roll, the ailerons act in opposing directions. Yaw, tail rudder turns left or right. Pitch, ailerons and horizontal stabilizer act together. So it is a roll maneuver that gives a plane a centripetal force, as we will see on the next slide. Okay, so as a plane rolls, the lift vector begins to have a horizontal component. So you can see, copy this free body diagram for this plane. This is a plane that's rolling, and this is just a vertical plane. So we can see now what the free body diagram looks like as a plane rolls side to side. The centripetal force causes the plane to begin traveling in a horizontal circle. We can see that is how a plane generates lift. Okay, so even though cars use friction, roads are banked so that the need for friction is reduced. This means that rather than a lift force, it's the component of the car's normal force that provides centripetal acceleration, that gives rise to the force. A banked curve can be designed so that a car can make the turn even if it is perfectly frictionless. The greater the angle, the greater the centripetal acceleration, the faster the car can travel. Thanks for watching. Study well.